In this video, you will learn how to use the Thevenin's theorem in solving electrical quantities or parameters in an electrical networks. Thevenin's theorem is one of the network laws and theorems that can be used in solving unknown quantities in a circuit. To properly introduce the Thevenin's theorem, it states that in any two-terminal network of fixed resistances and a constant sources of EMF, the current in a load resistor connected to the output terminals is equal to the current that would exist in the same resistor if it were connected in series with the simple EMF EO, whose voltage is measured at the open circuited network terminals, and a simple resistance RO, whose magnitude is that of the network looking back from the terminals into the network with all the sources of EMF replaced by their internal resistances. To realize this, we can have this Thevenin's equivalent circuit. So the EO here, the EO here is the open circuit Thevenin's voltage, this one, and RO is the looking back resistance or the open circuit Thevenin's resistance, and the RL is the load resistance. Now, if you want to find the value of the current RL, you need to have this equation. So IL is EO divided by RO plus RL. Actually, that's Ohm's law application. We need to find the total voltage of the circuit, then the total resistance. Okay, so the total resistance there is RO plus RL, since that is a series circuit. Now, okay, so in a given problem, we need to find the value of EO and RO. Then we connect it to the specific resistance or the load resistance in series. Okay, so we have an example here. Solve the value of current I in the figure below. So we need to solve this current here, in which the load is 5 ohm, and we have a supply of 24 volts. So we have 1 ohm, 2 ohm, 3 and 4 ohms, then 5 ohms at the center. So as a solution, first we need to solve the looking back resistance RO. So first you need to short circuit the 24 volts power supply. As you can see here, there are no power supply here, or there are no voltage applied to the circuit. Then open circuit the 5 ohm resistor. So this the 5 ohm resistor here was open circuited and solve the looking back resistance of this circuit. So as you can see, RO now is the looking back resistance. We need to find the value of our total resistance from these terminals. So as you can see, 1 ohm and 2 ohm are parallel combination, plus the parallel combination to the other side. Okay, so RO now, if you will compute this one, you will get an answer of 50 over 21 ohms. Next, solve for the open circuit voltage. So for the open circuit voltage, you need to put again the power supply voltage, then you open circuit the load, then replace it by EO. Then we have here an arbitrary current direction because you have a power supply load voltage source, so you have current here. So the current entering running here will go to this uh, junction or node, then it will be divided into two, I1 and I2. Okay, so first here we need to solve for the value of I1 and I2. I1 and I2. Now we can get that value because this is parallel. If we redraw the circuit, it's only uh, this one is equivalent to this one here. Sorry, uh, 24. Okay, this is 1 ohm, 2 ohm, 4 ohm, and 3 ohm. Since this is open circuit, so it is just like this one. Okay, so the voltage here in this part is equal to this part because that is parallel, and the total resistance is summation because this is open circuit, so it's just like unknown. Okay, so 4 and 3, then 1 and 2, so that's why I1 I1 here, I1, then I2 here, I2. So that is 24 divided 1 plus 2 equals to 8 amps. And I2 here is 24 divided 4 plus 3 is equal to 24 divided by 7 amperes. Now, if we go back to our circuit, we apply KVL, Kirchhoff's voltage law, on the loop A, A, B, C, and E. A. Okay, so EO, EO minus I2 times 4, because that's the voltage drop there, plus I1 times 1 equals to 0. Okay, so EO is equal to uh, I2 is 24 over 7. You substitute it here, also substitute it here. Now if we calculate that one, you will get an answer of 40 over 7 volts. So we have here the value of our EO and RO. Now for the step 3, we construct the Thevenin's equivalent circuit. So we have EO and RO, that is 40 over 7 and 50 over 21 for RO. Now it will be series to our load 5 ohm here, 5 ohm, and IL. So IL or I in our problem, that is I. We can also put here IL. Okay, so our load. So you just substitute the values EO divided by RO plus RL, that is 40 over 7 divided by 50 over 21 plus 5. And you will get the answer of 24 over 31 amperes. Okay, so that's how you use the Thevenin's theorem in a circuit. Thank you for listening, and I hope you learn something about this lecture. And if you have comments, you just leave it in the comment section. Thank you for watching this.